Hey, I hope everybody's well. Let's see, we were talking about multiple regression. That's where we are right now. In particular, we're talking about model building for the most part, which is a little bit, you know, deeper into multiple regression. In general, though, these are the kind of models we're dealing with. Right? We're talking about multiple regression, and we have made some assumptions. We're talking about stochastic relationships between one variable of interest, which we call the dependent variable, and usually we denote this with the letter y, dependent variable y, and then we have one or more independent variables or regressors. They're x's, and there are lots of names for these. They're called independent variables, they're called regressors, they're called right-hand side variables, they're called explanatory variables. It's a stochastic relationship, which means we have some error as well. But so far, all of our models look more or less like this. Let me pull up a different pen. We have a y on the left side. We have an intercept term, which is sort of like a baseline level. And then we have coefficients. These are the betas. And we have variables. Those are the x's. And then we got some dots. There are k different variables in our model, k different x's. Then we have the independent variable, or the dependent variable over here, and the error term over here. And that's what defines our model, right? Now, the problem is, or one of the problems, let me step back a second. So most of what we've been talking about has been what we call reduced form models, where we basically just throw a model in, a variable in on the left side, and then we throw a bunch of variables in on the right side. And we haven't been motivating this stuff with theory very much. We'll talk a little bit more about how theory can motivate this, right? So how whatever the way you understand the world, how that dictates how you should set up your model. But one of the things we want to be able to do is we want to be able to take two models that might be very similar and compare them to see if one is better than the other. And one way that we've done this sort of roughly so far has been using adjusted R squared. Adjusted R squared isn't bad. The adjusted R squared tells us about one dimension, right? This is it's goodness of fit of the model, or the explanatory power of the model. It's another way to think about that. And it just tells us, with some penalty, right? We talked about how to get the adjusted R squared in a different video, so I recommend going back and looking if that's unfamiliar to you. It tells us with some trade-off for increasing the number of regressors, how much of the variation in y we have explained. So that's how much of the variation. That's why we call it explanatory power. Another way to think of it is how well it fits the data. Now that can be very unuseful, right? I mean, if you regress your age on the number of years you've been alive, that's trivial. But in some cases, that can tell us a lot. There's a very good test for a specific case, though. So what we're going to do is we're going to look at two models here. Let's say we have two models, and what we're trying to do is we're trying to estimate costs at a manufacturing plant. So we're doing cost estimation. Very common scenario. We're trying to estimate cost, and we have two models. One is simple. Okay, this one contains units produced and labor hours provided. Okay. Let's say that the other one is more complicated. It contains these two things, right? So it contains x1 and x2, which are going to be units produced and labor hours. But it also contains a bunch of other stuff. Let's say quantities of intermediate goods, right, like plywood. The amount spent on bathroom repairs. You can just put repair costs. Lots of other stuff that go into this, right? So you can just imagine, I'm going to put just ... It has a lot of stuff in there. So the question we're going to ask ourselves is it worth the time and effort to collect this extra data? And very specifically, does the second model do a better job? Does the second model significantly improve our regression? And what we're really asking essentially is, does it provide a better fit? So that's what we're going to ask. That's what we're going to look at. There's a very straightforward way to test for this. And it works in any time we have this case, right? We've looked at tests of significance. We've looked at regression, residual plots. Well, if you haven't looked at residual plots, I will be posting a video on that soon, but there's already some practice videos up there. We've made judgment calls. But when the two models directly overlap, so that's the case we're looking at, when two models directly overlap, meaning one contains a subset, a proper subset of the other one, you can test to see if overlap, if one does a better, if the full model does a better job. So what do we have? Well, we have two models. One contains, say, Q regressors. That's the smaller model. Call this reduced. And one contains Q, these Q, and more, for a total of P regressors. And this is the full model. We can test to see if the full model does a better job than the reduced model of explaining the data. So our first model, to be very general, I'm not looking at the specific case anymore, is going to look like this. Y equals beta 0 plus beta 1 x1 plus beta 2 x2 plus dot 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 plus beta q xq plus epsilon. Okay. And that's the reduced model again. It only has Q regressors, and Q is less than P in this case. Our second model, change colors again, so we have these separate. Our second model looks like this. Y equals beta 0 plus beta 1 x1 plus beta 2 x2. And these are the same x's. Plus dot 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 plus beta q xq plus beta q plus 1 xq plus 1 plus beta q plus 2 xq plus 2 plus dot 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 plus beta p xp. That doesn't have to be this many. I mean, you can look at a model with one regressor versus a model with two regressors, or a model with three regressors versus a model with five regressors. But these are what the models look like. So this one's going to be our full model. It contains the kitchen, sometimes it might be called a kitchen sink model. And this is the reduced model right here. Reduced. Okay, now what we're trying to do is we're trying to see if these essentially are of any use. These q plus 1, all the extra ones, this is a 2 by the way, q plus 2, p, all these ones. We want to know if they provide any value. So this is just a hypothesis test. And ultimately what we're doing is we're looking at the amount of variation that we've explained. And so this is going to be a test of two variances, basically. I'll walk you through what it looks like, but the reason that we're going to use an F statistic, and the reason we're going to use an F statistic is that we're trying to see if essentially the bonus variation we've explained is significant. All right, now putting on our hypothesis testing hats, we have the 5-step process. The first one is to formulate our hypotheses. And again, as always, our null hypothesis goes first, and we have an alternative. And our null here is that these don't matter. Beta q plus 1 plus beta q, or equals beta q plus 2 equals dot 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 equals beta p equals 0, which is to say that all the new coefficients are 0, which is to say that none of the new regressors have any relationship with y. That's essentially what we're saying. And then HA, our alternative, is saying that at least 1 beta I for I greater than q is not equal to 0, meaning that one of these coefficients is different from 0, where we're only talking about the coefficients for the new variables that we've thrown in. I hope that makes sense. So this is just like an F test of joint significance, but it's joint significance for a subset of variables, and that's what this is actually called. This is an F test for joint significance of a subset of variables for a subset. And if you want to know if a group of variables are significant, you can do it this way as well. I mean, the way that I've presented this is as a means to compare two models, but you can do it just to check if you have 3 or 4 variables that you've thrown in that you're not sure if they're significant. If you want to test to see if they are significant, this is a way to do it. Step 2, as always, is to choose your level of significance. Pretty standard is 0.05, but you can choose whatever you want. Not whatever you want, but yeah, choose a reasonable level of significance. Do what your boss tells you. Step 3 is our test statistic, to choose a test statistic. And this is what our test statistic looks like. F equals, okay, it's a big fraction, and on top is another fraction. So up here we have the SSE, the sum of squared errors for our reduced model. It says reduced. If you can, man. Minus the sum of squared errors for our full model. And this is always going to be positive, right? Because our full model is going to have less error than our reduced model because it has more explanatory variables. It always has a better fit. The question is this difference big enough? And essentially, well, under here, what we're going to do is we're going to put the number of extra regressors, which is P minus Q, but I think it's easier to understand it intuitively. P minus Q, right, is that difference. And the way to think about this top part, right, because this can go in parentheses, this is on top of a big fraction, is it's sort of like an MSE for the new regressors alone, right? So how much variation on average does each of the new regressors explain? And then we have the MSE, on the bottom we have the MSE of the full model, which is sort of the average explanatory power of a regressor if you include all of them. And so we're kind of measuring, how much better than average do these do. Okay. So this right here is P minus Q. That's where that comes from. But this is off to the side, separate in a little explanatory box, because this right here is just your test statistic. Okay, it's going to be the difference in the sum of squared errors divided by the number of extra regressors, and that's the top, all divided by the mean square error of the full model. And again, you can pull those right. These things all come from right from the Excel output. Here you're going to have to actually figure out what these two are, right? You figure out how many regressors you had in the full model. That's P, and then you figure out how many regressors you had in the reduced model. That's Q, and that's how many extra regressors you have. Okay, now under the null, this has an F distribution. How many degrees of freedom does it have? Well, it has P minus Q degrees of freedom in the numerator, so the number of extra regressors is the DF numer. That's degrees of freedom in the numerator, and N minus P minus 1 in the denominator, which is to say this is the N minus K minus 1 for the full model. It's the degrees of freedom, it's the DF residual in your full model. So if you see the degrees of freedom column and the residual row, then that's where you're getting this. So what would this look like? Well, if you had, let's say you had 50 observations, okay, and you had your reduced model had 2 regressors, and your full model had 4 regressors. And you want to know if those those extra 2 that you've added are of any use. Well, what you're going to do is you're going to run those regressions. You're going to take the sum of squared errors from the reduced model, subtract the sum of squared errors from the full model, and then divide by 2, because that's your number of extra regressors. And then you're going to divide that by the MSE from the full model, which you can just, again, pull from the Excel output. And then under the null, this is going to have this distribution. You have 2 extra, it's going to be F, sorry, this should be F. It's going to have 2 extra regressors, so we have 2 degrees of freedom in the numerator, and then we have 50 minus 4 minus 1, so that's 45 degrees of freedom in the denominator. And that'll be your, that's the degrees of freedom for your F distribution. That is your F distribution right there. And so you get the statistic, and you just, it's always upper tail, as these things are. That's good, important to note, as these F tests are. It's always going to be upper tail, but once you do that, you calculate it. That's step 4. Step 5 is just to do your inference like we've done before. Pull out your F table and get familiar with it. And there should be an example practice problem that we've seen before, or that's posted online. So if you have any questions about how to do this, again, you're going to use this whenever you want to compare 2 models where one is a perfect subset of the other. So when 2 models directly overlap, that's when you want to use this. And when you do that, you can just do an F test and come up with a responsible conclusion about how likely it is. If you reject the null, you can conclude that one of them is at least one of them is valuable, right? That's to say that the full model does a better job than the reduced model because of these extra regressors that you've included. If you fail to reject the null, you can basically say that including these extra variables, um, you can't conclude that it provides any extra benefit, right? Okay. So, yeah, once again, you have any questions, please post a comment or email me at jjdelaney@ualr.edu, and I'll be happy to get back to you. Thanks. See you soon, guys. Bye.